Hello everyone, so welcome back to lecture 2 on this chapter on the reactivity series of metals. Now in lecture 1, we have covered the structure and physical properties of pure metals, and we also talked about alloys, and we moved on to this important concept of the reactivity series of metals. We also used the reactivity of series of metals to order the metals in order of reactivity, and we learned about the reactions of the metals with cold water and steam. So we have already covered page 1 to 11 of this set of notes in lecture video 1. So if you are unclear about anything from page 1 to 11, please go back to lecture video 1 and revise from there. And do ask me questions whenever you have any doubts. For this video, we're going to go deeper into the reactions of metals. Some of these reactions will look familiar, as you can see on the screen right now, is acid plus metal. Okay, so today we will aim to cover pages 12 till 16. Now, one note about today. I want us to use the redox lens to view all the reactions today. Meaning, as we go through the reactions, may I encourage all of us to think through what is reduced, what's oxidized. Can you explain that in terms of oxidation states? Okay, so if we are ready, let's start with page 12. Now, on page 12, we see an old reaction here. We have all learned this. It's the reaction of acid plus metal. Now, specifically over here, I have chosen hydrochloric acid, HCl. So what does this form? Acid plus metal forms salt and hydrogen. Because I've chosen HCl, the salt will be the metal chloride. So if you recall, for example, magnesium reacts with HCl to form magnesium chloride and hydrogen gas. Okay, now which metals are able to react with acid? I think this one we are very clear. To identify which metals react with acid, we look for hydrogen. So hydrogen, where is it in the reactivity series? It's just above copper, meaning anything above hydrogen, it can react with acid. So potassium, sodium, calcium, magnesium, all the way till lead will be able to react with acid. This is because these metals are above hydrogen in the reactivity series. However, if they are below hydrogen, such as copper and silver, they do not react with acid. Okay, so this is something for us to take note of. Copper and silver do not react with acid. So I would like us to put a cross there to be very clear about it. Okay, now this is very important. We will need to know which metals are unreactive with acid. And why are they unreactive? Because they are below hydrogen in the reactivity series. Okay, so very often we are asked to explain in terms of the position in the reactivity series. So if it's below hydrogen, that's the position, it will not react with acid. So now, potassium and sodium, we will not react them with acids because they are explosive with acids. So let's begin with calcium. Calcium reacts very violently with acids. And this produces calcium chloride because it's HCl. All right, so I'm sure you can write this equation relatively quickly now. So solid calcium metal reacts with HCl, aqueous, to form CaCl2 aqueous plus hydrogen gas. Now, this reaction itself is very, very violent. You will see very, very vigorous effervescence. All right, very vigorous effervescence. So in fact, calcium, we usually do not react it with HCl either. Okay. Now next we go to magnesium. So we have learned this before in lecture video 1. If the first metal is very violent, one notch below that should be violent. So magnesium reacts violently with HCl to form magnesium chloride and hydrogen gas. So again, the equations are balanced relatively similarly. Okay. So that is magnesium plus HCl. This is commonly done in the lab. We have done this a number of times already. Okay, you will see vigorous effervescence. This tells you that hydrogen gas is being produced relatively quickly. Now, moving on, we have zinc plus HCl. Zinc reacts readily with acids, in this case HCl, so it produces zinc chloride. So you notice that these metals, they all form the 2 plus charge in their ionic compounds. So we have Ca2 plus, Mg2 plus, and now we have Zn2 plus. And hence the equations are balanced very similarly because the chemical formula of the salt is the same. Iron. Iron reacts slowly with acids, and in this case, it forms iron 2 chloride. All right, FeCl2. So for iron, it always forms the Fe2 plus first. All right, so this is an important thing to learn. For iron, I'm sure you remember from redox, you have already seen iron 2 plus and iron 3 plus. Apologies, it's supposed to be aqueous. FeCl2 aqueous plus H2 gas. So there's Fe2 plus and there's Fe3 plus. So generally, we will form Fe2 plus first. Okay? So it forms iron 2 chloride first. Now, iron 2 chloride is a green solution. So you can actually see the solution turning a pale green as iron starts to react slowly with HCl. All right? Now, if this solution is left standing in air, that means if it's left open to the air, this can be oxidized by air. So that's a separate reaction. It can be oxidized by air to form FeCl3. It's a separate reaction, so you do not write it as part of the equation. I am just telling you that FeCl2 or Fe2 plus in general can be oxidized by air to form FeCl3. Now, FeCl3 is a reddish brown solution. So you will see that the green solution of iron 2 chloride does turn slightly yellow, if not reddish brown. And this is because the Fe2 plus is oxidized by oxygen in the air to form Fe3 plus. So depending on the oxidation state, the metal actually may demonstrate different colors in its compound. So Fe2 plus tends to be green. So anything with Fe2 plus tends to be green, whereas anything with Fe3 plus tends to be reddish brown. Okay? Now, finally, we come to lead. Now, lead reacts very slowly with acids. This is because lead is below iron in the reactivity series and is even less reactive than iron. So we can expect lead to react very, very slowly. And what's important is the reaction stops completely after a short time. So again, this is something that we need to take note of. Why would it start and then suddenly the reaction stops completely? Now, the reaction stops completely because you are forming something insoluble. So in this case, if you recall your solubility rules, lead 2 chloride is one of the chlorides which is insoluble in water. So when lead reacts with HCl, it starts to form lead 2 chloride. And because the lead 2 chloride is insoluble, it will start to coat the surface of the lead metal. So it coats the surface of the lead metal and it prevents the metal beneath the insoluble precipitate from reacting further. It stops the reaction. And this is the reason why we do not use lead metal with HCl to make insoluble lead 2 chloride. Lead 2 chloride has to be made by precipitation method, not acid plus metal. The reason is because lead metal would form the insoluble PbCl2, which stops the reaction. Okay, so this reaction should already be familiar to us. This is acid plus metal. Okay, now I would advise us to revise acid plus metal. If you have forgotten what is the test for hydrogen gas, please go back to acids and bases. If you have forgotten how to write these equations, please revise acids and bases to recap how to balance these equations. In addition, if we have forgotten solubility rules in salt prep, please revise salt prep and please think through why lead 2 chloride is not made by acid plus metal. Okay, it's an insoluble salt. It needs to be made by precipitation. All right. Now, moving on, the next reaction that I'm going to move on to is a very important reaction. It's called displacement reaction of metals. It's a very simple concept. All right. So please follow me. So what happens is if I add magnesium metal to copper 2 sulfate. So at first, I have Mg alone, standalone, and I have copper 2 sulfate. So the copper 2 ion is joined to the sulfate ion, is bonded by strong electrostatic forces of attraction, right? So at first, magnesium is alone, copper is part of the compound, it's part of the salt. When I add the magnesium metal into copper 2 sulfate, something amazing happens. All right. What is this thing that happens? Magnesium is able to displace copper. It's able to kick copper out from the compound. At first, copper and sulfate are together. Magnesium, as the third party, comes in and kicks copper out. This kicking out of copper is called displacement. We say that magnesium can displace copper from its compound. Copper was together with sulfate, it got displaced by magnesium. Why is magnesium able to displace copper from its compound? Magnesium can displace copper because magnesium is more reactive than copper. So what happens now is at first copper is together with sulfate. Now copper is kicked out on its own. Magnesium was alone at first. Now magnesium snatches the sulfate over and bonds to sulfate instead. And all this is simply because magnesium is more reactive than copper. Therefore, magnesium can displace copper from its compound. So if we were to generalize this rule, we can say that a more reactive metal displaces a less reactive metal from its compound. Every single time we have a more reactive metal, it's able to displace a less reactive metal that was bonded to something else. Okay, so like in this case, magnesium can displace copper from copper to sulfate. Copper to sulfate is compound of sulfur, of copper, sorry. Okay, now, like I said, let's put on our redox lens and analyze this from a redox lens. So if we look at the equations now, can you work out what's reduced and what's oxidized? So if it's easier, we could use the ionic equation for displacement to help us. So I have the chemical equation on top. I have the ionic equation below. All right. So you can clearly see that the sulfate ion is not in the ionic equation. The sulfate ion is not in the ionic equation because the sulfate ion is a spectator ion. The sulfate ion doesn't change during the reaction. Therefore, spectator ions, as we have learned, are excluded from the ionic equation. So we literally cancel out the sulfate from the chemical equation to make the ionic equation. So if you look at the ionic equation, it becomes clear what is oxidized. Mg is oxidized as the oxidation state of magnesium increased. And it increased from what? It increased from 0 in Mg to +2 in Mg2 plus. Okay, this is one way to use oxidation states to explain that magnesium is oxidized. And because Mg is oxidized, Mg is the reducing agent. All right. So we can clearly see that magnesium metal, in this case, is the reducing agent that causes Cu2 plus to be reduced. Okay, I will not write the sentence for Cu2 plus is reduced. I will leave it up to you to try it. You will also try this out extensively in tutorial 2, which you will do. Tutorial 2 centers around the idea of displacement reactions. Okay, so what can we learn from this? We can learn a few things from this. Number one, the more reactive metal going in is going to displace the less reactive metal from its compound. So if a less reactive metal was bonded to sulfate, the less reactive metal is going to get kicked out. It's going to get displaced. Get out. All right. So the more reactive metal has the power to actually displace the less reactive metal from its compound. And this is a redox reaction where you can see, using this example, magnesium is oxidized as the oxidation state of magnesium increases from 0 in Mg to +2 in Mg2 plus. So magnesium is the reducing agent. If I were to extend this logic, we can conclude the more reactive metal is always oxidized. So magnesium metal is oxidized in the displacement reaction. All right. Now, this displacement reaction is quite famous and it's quite interesting to do in the lab. Okay. We will actually do this in the lab when I come back from my course. But the idea behind it is really, really simple. It is simply about the reactivity series. More reactive metals, as their name suggests, really want to react. How do they react? They react by losing the electrons they have. So magnesium wants to lose the 2 valence electrons much, much more than copper wants to lose electrons. So magnesium is reactive. It wants to lose 2 valence electrons. That's why magnesium is more easily oxidized. And that's why magnesium can displace copper, because magnesium wants to form Mg2 plus and be with sulfate. It wants to bond to sulfate more than Cu2 plus wants to bond to sulfate. And that is the idea of metal reactivity. Okay? Now, this reaction is also very famous to do because you actually see copper metal being formed. Now, copper metal is quite an interesting color, as can be seen on the bullet points there. The copper metal forms a solid deposit. Now, this is not a precipitate. Precipitate refers to a solid as insoluble, but solid deposit is something even more specific. Deposit means it sticks onto the surface of the metal. So copper metal tends to stick onto the surface of the beaker or stick onto the surface of the magnesium which you have added. All right. So this is a reddish brown solid deposit. Now, copper metal tends to be reddish brown in color. It's not silvery. Okay, most metals are silvery except copper metal and gold metal. All right. So copper metal is a reddish brown solid deposit. At the same time, copper 2 sulfate is blue in color, but magnesium sulfate solution is colorless. So the color change that you will observe is blue color forming a colorless solution. So the blue color of the solution fades over time. And this is because the Cu2 plus is being displaced to form copper metal. In its place, you get magnesium sulfate. Magnesium sulfate forms a colorless solution. Now, don't worry too much about the color changes. We would learn them slowly after EYE when we learn the chapter on qualitative analysis. But for now, I think it suffices to learn the color of copper metal is a reddish brown solid deposit. And you should also learn that copper 2 sulfate is a blue color solution. Okay? Now, let's watch a short YouTube video. There's no sound for 1 minute to see what this displacement reaction looks like. Now, in this YouTube video, the scientist is actually using iron to displace copper. So, iron plus copper 2 sulfate. Now, is there a reaction? Think about it. Iron plus copper 2 sulfate. Is there a reaction? The answer is, let's think through. Iron is more reactive than copper. Copper is less reactive. So iron is able to displace copper from copper 2 sulfate. So there is a reaction. This forms FeSO4 plus Cu. So it forms iron 2 sulfate and copper metal. So we should expect to see copper metal form. And if you recall, copper metal has a reddish brown color. So let's see if we get any solid reddish brown copper metal when we put iron into copper 2 sulfate. Okay, so this is copper 2 sulfate. As you can see, it's very blue. It's a very blue solution. This is copper 2 sulfate. Okay, so as you can see, we're going to pour some of the copper 2 sulfate out. And that forms a very nice blue colored solution. So this is what copper 2 sulfate looks like originally. Now we are going to lower into copper 2 sulfate an iron nail. This is Fe. And we're just going to wait a little bit and watch what happens. Now, immediately you can already start to see some changes. You can see that on the surface of the iron nail, there is a reddish brown solid deposit forming. What is this reddish brown solid deposit? This reddish brown solid deposit is actually copper metal. This is copper metal itself. So how did the copper metal come about? It came about because the iron is more reactive than copper. Because the iron is more reactive than copper metal, it's able to actually displace copper from copper 2 sulfate, and that forms Cu, metal itself. Okay, so you can clearly see the reddish brown solid deposit forming on the outside. At the same time, you can begin to see a change in the color of the solution. I'm sure you will agree with me. At the start, the copper 2 sulfate solution looked really blue. It looked like the concentration of copper 2 sulfate was high. It looks really, really blue. But now as the reaction proceeds, you can clearly see the solution has changed color. In particular, the blue color of the solution is fading away. It's much less blue than it was before. All right. So now returning to our notes. Now we understand redox. Now don't worry too much about this table. Having said that, we are now going to learn how to interpret such data to actually work out which metal is more reactive. So if we turn to the example question. In the example question, this is quite it resembles exam style questions for pure chem as well as combined science for displacement reaction of metals. So you are told 4 metals, PQRS, are separately reacted with solutions of 4 metal sulfates. Metal sulfates. Metal sulfate. This is a compound. These are metals. I'm testing whether metal PQRS could displace these metals from their compounds. Okay, a tick indicates the metal has reacted. A tick indicates the metal has reacted means there is displacement. If there is a tick. Conversely, a cross indicates that no displacement, no reaction has taken place. So now how do we interpret this? Mr. So will always do this. I will highlight the metal first. Always highlight the metal first. And then now let's look across the row. Okay? P. What is P? P, 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 P. All right? So what am I doing? I'm actually going to look at how many ticks it has. P only has 1 tick. What does this mean? It means that P can only displace. Sorry, maybe I should write on top. P can only displace copper. P displaces copper. Not magnesium, not iron, not zinc. P can only displace copper. How about Q? Q has 4 ticks. What does that mean? It means that metal Q could displace copper, magnesium, iron, zinc. Copper, magnesium, iron, zinc. Q displaces all 4 metals that you have been given in the sulfate. Now, this is significant. Remember, what can displace what? The rule is the more reactive metal displaces the less reactive metal from its compound. This means that Q should be more reactive than copper, magnesium, iron, and zinc. Q is more reactive than all 4 of these metals. All right. Then we come to R. R is all cross. No displacement. R cannot even displace copper. R is less reactive than copper, magnesium, iron, and zinc. R can't displace anything. Finally, we come to S. What can S displace? S can displace copper, iron, and zinc. Okay, so with that, I think it becomes quite clear-cut. How can we rank these four metals in order of increasing reactivity? Increasing. Increase means from lowest to highest. This is the meaning of the word increasing. Now, it's very important to know such English words because you'll be asked to do ranking of metals in order of increasing or decreasing reactivity. So you need to be sensitive. Increasing means we start with the lowest reactivity. And the lowest, of course, is R. This is because it couldn't displace anything. So R must be the least lowest reactivity. Next, what is the next most reactive? P. P can displace copper only. All right. So P is more reactive than copper, but less reactive than magnesium, iron, and zinc. Then we come to S. S can displace three of the metals, copper, iron, and zinc, but not magnesium. Finally, and lastly, the most highest reactivity metal here is Q. Q is the most reactive because it could displace all four of the metals, copper, magnesium, iron, zinc. Okay, so this is a very, very common data table. You must know how to interpret this. Now next, describe what will be observed when a strip of metal P is placed into copper 2 sulfate. So we have learned this just now. If there is displacement, you should expect the metal copper to be formed. And copper is very special because copper forms a reddish brown solid deposit of copper metal. All right, so it forms a reddish brown solid deposit of copper metal. What else? Just now in the YouTube short video, we actually observed copper 2 sulfate is very special because it's a blue solution. But as the reaction proceeds, the blue color of the solution fades. Okay? So this is a very typical displacement of metal questions, which I will really, really advise us to practice in tutorial 2. All right? Now, finally, like I said, let's talk about redox. I would like us to really try out part C and think through this reaction between P and copper 2 sulfate from the perspective of redox. So let's revise once more. So this is the ionic equation. We have given you the ionic equation. You can clearly see that P is more reactive because it has displaced copper from its compound. Now, how do you know whether something is a compound or not from an ionic equation? If it's charged, it's an ion. It is part of an ionic compound. So when you see Cu2 plus, Cu2 plus is actually part of an ionic compound. Okay. Similarly, you have P2 plus. P2 plus is part of an ionic compound as well. So you recognize that something is a compound when it has charge in the ionic equation. If it's in the ionic equation and it has charge, it's a compound. All right. Conversely, if it doesn't have charge, it's now on its own as an element. So P at the start is an element, Cu at the end is an element. Okay? Element. No charge. All right. Now, this question in part C requires us to use ideas about electron transfer to explain which substance has been oxidized or reduced. This is a good opportunity to revise redox. Remember, I told you all before WA3 that redox is the foundation for metals. Now you can see why. So, what is about electrons? Remember, oil rig, oxidation is loss of electron, reduction is gain of electrons. So, what has P done? P is oxidized. How can you tell? As P lost 2 electrons to form P2 plus. Remember, when you lose electrons, you become more positive. Losing electrons makes you more positive, and therefore we can tell that P is oxidized because it lost 2 electrons. Conversely, Cu2 plus is reduced as it gained 2 electrons to form the copper metal, Cu. So it became less positive. To become less positive, you must gain the electrons. Okay? Now, let's also practice writing the half equations. Wow, what is half equations? So if you recall, in redox, we learned something wants to form P2 plus. P forms P2 plus. How many electrons are lost? 2 electrons are lost. Now, the half equations are the equations which show you the electrons being lost or gained. So if the electrons are lost, they will be on the right-hand side. So electrons are lost means electrons on the right-hand side means oxidized. Okay? So how then do we write the reduction half equation? To write the reduction half equation, we simply look at Cu2 plus. Cu2 plus gain 2 electrons and form copper solid metal. So this, you can see the electrons are on the left-hand side, meaning electrons are gained. Hence, this is a reduction half equation. So you can see that every ionic equation for redox has an oxidation half equation and also has a reduction half equation. So this is a key skill that we can practice using the lenses of displacement reactions of metals. And this is what I would strongly encourage all of us to be familiar with. I'm going to keep this screen here for a little bit of time. Please pause and copy everything down and ensure you are thinking about redox right now. Okay, I would really like for us to think about redox. And at the end of this lecture, you should be able to talk about displacement reactions in terms of oxidation states as well as electrons. And you should be able to write the oxidation half equation and the reduction half equation. So please pause here and reflect and revise if needed. Okay, now we shall move on and look at even more examples of displacement reactions. Must we always displace the less reactive metal from a sulfate? Can't we displace the less reactive metal from its other compounds? Well, you can, because the rule is just that a more reactive metal displaces a less reactive metal from its compound. It doesn't need to be a sulfate. How about oxide? Oxides are also compounds, and indeed, if you look at this reaction, zinc plus copper 2 oxide, zinc metal is more reactive than copper. We know this because zinc is above copper in the reactivity series. So zinc is more reactive. So zinc could displace copper from copper to oxide. All right, and that's exactly what happens. At first, copper and oxide ions are bonded together. Now copper is left on its own. So again, this is a displacement reaction. And you can also examine this from a redox viewpoint. All right. Now, this reaction is very easy to do. All you need to do is to mix zinc with copper 2 oxide together in a crucible. Now, a crucible basically is a container that is heat proof. It doesn't melt, so it can be heated up to a very high temperature and it still won't melt. And that's important because this particular displacement reaction between zinc and copper 2 oxide releases a lot of heat. Okay, so it gets really hot. All right. Now, you also need sand. The sand doesn't do anything. The sand prevents fires. It stops the fire from spreading. Again, like I said, this reaction is super, super hot. So things will start to catch fire. You need to have something to stop the fire from spreading, and that's sand. All right. But the most important thing we need to know here is zinc powder plus copper 2 oxide. This is a displacement reaction. It works because zinc is more reactive than copper. All right, so you can displace copper from copper 2 oxide. And now we come to redox time once more. So what is oxidized and what's reduced? Can you work it out? I will give you some time. You want to pause the video here and work out what's reduced and what's oxidized. Okay, I hope you have had some time to think through it. You will realize that zinc is oxidized, and let's use oxidation states to explain this. Zinc is oxidized as the oxidation state of zinc increases from 0 in Zn to +2 in ZnO. All right, so zinc is oxidized. Therefore, zinc is the reducing agent. Okay, zinc is the reducing agent. You would have realized that copper 2 oxide is reduced as the oxidation state of copper decreases from +2 in CuO to 0 in Cu. Okay, so that tells you that copper 2 oxide is reduced. So CuO is therefore the oxidizing agent because it's itself reduced. All right. Hence, through this redox lens, we can see that, hey, displacements are everywhere. And displacement is simply based on reactivity of the two metals. Zinc is more reactive than copper, so zinc displaces copper. And displacements are all redox reactions. And that's the link between redox, the previous chapter, and this chapter. All right. Now, since zinc is the reducing agent, we can also say that zinc reduces copper 2 oxide. So this is the reduction of copper 2 oxide by zinc. So we can take this down. Another way to phrase this redox explanation, zinc reduces copper 2 oxide. This is the reduction of copper 2 oxide by zinc. And it works. Zinc can reduce copper 2 oxide because zinc is more reactive than copper. Okay, this is possible because zinc is more reactive than copper. So it can displace copper from copper 2 oxide. It could reduce copper 2 oxide to copper. So do you realize now, saying that something can displace the metal is the same as saying it could reduce the metal ion back to the metal. That's the linkage. All right. Now, there are more examples of all sorts of displacements like this. So instead of zinc and copper, how about aluminium and iron? Indeed, this works as well, right? Aluminium, again, in the reactivity series, is higher than iron. Aluminium is more reactive than iron. Because aluminium is more reactive than iron, it could displace iron from iron 3 oxide. This works. It's a perfectly valid displacement reaction. So this is the equation for it. Now, this displacement can also be analyzed from a redox standpoint. I would strongly encourage all of us to use oxidation states to actually explain what is reduced, what's oxidized. What's the reducing agent? What's the oxidizing agent? Now, this reaction is very, very exothermic. What is exothermic? We have learned this in chapter 2 in kinetic particle theory. Exothermic reactions are reactions that release heat energy to the surroundings. Now, this particular displacement between aluminum and iron 3 oxide is so exothermic, it releases so much heat that the iron that's formed actually melts. That's why the state symbol is a liquid. It's a liquid because it's so hot that the iron has melted to form molten iron. All right. So the molten iron flows like a river of lava. But this lava is not water, it's actually molten liquid iron metal. Now, this is really useful because it allows you to join together segments of metals, particularly joining rail segments together. So when you manufacture railway tracks, you can't manufacture the whole track as a 100-kilometer stretch. You can only manufacture perhaps every 100 meter. But every 100 meter needs to be joined together, right? The segments have to be joined together to form a continuous rail for the trains to move. How do you glue the segments together? You can't use super glue. So the glue here is actually the molten iron. So this reaction is called the thermite reaction. It allows you to form molten iron, which flows into the gaps between the rail segments. When it cools down, the molten iron obviously solidifies. It freezes to form solid iron, and that holds the tracks together. All right. So this reaction is called the thermite reaction. I would strongly encourage us to watch this video in OneNote to the right-hand side of this set of notes. It's really, really fascinating to learn more about this reaction. Now, you must be wondering, what on earth is this magnesium fused for? Is magnesium involved in the equation or the reaction? No. Magnesium simply provides the initial spark to start the reaction. So the magnesium here is not really performing a role. The magnesium here is just to spark off the reaction. Okay? All right. This is displacement, reduction as well of the metal oxide by a more reactive metal. It's a displacement. Let's look at even more displacements. How about carbon? Carbon is also in the reactivity series, right? If we write out the reactivity series from memory, which I hope you can do by now, carbon is in the reactivity series. Now I'm writing out the reactivity series. You notice that carbon is located here. This is important because this means that carbon can actually displace some of the metals from their compounds. So which metals could carbon displace? Remember, higher up means more reactive. So carbon is higher up than these metals. Carbon is higher up than these metals that I have shown you. These metals are below carbon. If the metals are below carbon, they can be displaced or reduced by carbon. So for instance, copper, again, copper 2 oxide can be reduced by carbon because copper is below carbon. In the reactivity series. Because it's below carbon, it can be reduced by carbon. Okay, so carbon reduces CuO to form Cu. In the process, carbon is oxidized to form CO2. How do you know that CO2 is formed from this reaction? Simply bubble the gas into lime water. So what would you notice here? You will notice a white precipitate formed in lime water. And this confirms that CO2 gas has been formed. Okay? And that is a good example of another displacement reaction. And this time round, it's not even a metal, it's actually carbon being able to reduce the metals below carbon. Now, metals above carbon, such as potassium, sodium, calcium, magnesium, aluminium, if it's above carbon, it cannot be reduced by carbon. So, for example, if I were to heat up magnesium oxide with carbon, so MgO plus carbon, is there a reaction? No. There's no reaction possible because magnesium is above carbon in the reactivity series, and so it cannot be reduced by carbon. All right. Now, the last reduction of metal oxide by hydrogen reaction. This is slightly peculiar. Hydrogen is also able to reduce the oxides of less reactive metals. Basically, oxides above iron, metals above iron cannot be reduced by hydrogen. Now, this proceeds in a similar fashion to how carbon works. Okay, but you might notice hydrogen a bit strange. Why is it iron can actually be reduced by hydrogen? It's all about heating and temperature. To reduce iron from iron oxide by hydrogen, you need a higher temperature. All right. So for this, you will unfortunately need to memorize those metals above iron cannot be reduced by hydrogen. They are unaffected by hydrogen. Those metals below iron can be reduced by hydrogen. All right. So this shown here is an example. And of course, hydrogen now forms steam, H2O. All right. Now, so again, this is yet another displacement, right? You can clearly see that hydrogen has reduced copper 2 oxide to copper, or hydrogen has displaced copper from the oxide. Okay? Now, this is the setup. As you can see, we have zinc powder and sulfuric acid. This is acid plus metal, clearly. And this produces hydrogen gas. So why do we use this to produce hydrogen gas and not just connect it to a hydrogen gas tank? The reason why we actually generate hydrogen gas like this instead of wiring it to a gas tank directly is simply because hydrogen gas tanks are dangerous. We don't usually store hydrogen gas tanks in the lab because hydrogen is explosive. Storing it in a tank for too long runs the risk of something exploding. And therefore, we typically generate and produce hydrogen gas when we need it. So only when we need it, then we produce the hydrogen. And this acid plus metal is a good way to produce hydrogen. So the hydrogen is produced and will travel up into the reaction tube where you have zinc oxide and copper 2 oxide. Now, zinc oxide, zinc is above iron. Zinc oxide is unaffected by hydrogen because zinc metal is above iron, so it cannot be reduced by hydrogen. However, copper 2 oxide is reduced by hydrogen to Cu metal. Okay? Now, so the hydrogen forms H2O, which can be condensed as a liquid. So W here is water, right? Now, importantly as well, whenever you do hydrogen, you must remember, keep the hydrogen gas flowing even when heating is turned off. Now, in this case, why? Why must you keep the hydrogen gas flowing by adding more acid and metal together? Why must you keep the hydrogen gas going through even when the heating is off? Now, when the heating is turned off, the copper is still very hot. You need to ensure the copper metal does not react with the air. Imagine if the hot copper metal reacts with oxygen in the air. It will form back copper 2 oxide. which is a waste of your time, right? You wanted the copper 2 oxide to be reduced to copper. Why would it want the copper to react again, to go backwards? You don't want that. So this is to ensure the copper metal continues to stay as it is, don't react with the air. All right, especially when it's hot. When it's hot, copper metal can react with air. So while waiting for it to cool down by switching off the heating, please keep the hydrogen gas flowing so that air doesn't enter the setup. When air enters, the copper metal will react with oxygen in the air to form back copper 2 oxide, which will waste your effort. Okay? Now, this brings us to the end of a rather content-heavy lesson once more. Today, our main learning point, acid plus metal and displacement reactions. And as you have seen, displacement has so many examples, be it reduction of metal oxide with carbon and hydrogen, or reduction of metal oxide with a more reactive metal. And these displacement reactions, they are all redox reactions. So in tutorial 2, I would like for us to practice displacement as well as redox at the same time. When you practice redox, I hope by the end of today, you are able to explain the displacement reaction both in terms of oxidation states and electrons. And I hope you can write the oxidation half equations and reduction half equations. All right. Now, please stay tuned for lecture video 3, which will be a lot shorter because actually you are done with the most difficult concept in metals already. Now, this is the end of lecture video 2. Please revise displacement reactions and redox thoroughly because this is actually the key part of this chapter. Okay, thank you and see you in lecture video 3.